Watch what happens when we pour honey and machine oil down a smooth surface at the exact same time. Both of these substances are liquids. Both are being pulled downward by the exact same gravitational force. Yet the machine oil glides effortlessly down the incline, while the honey visibly stretches, lags, and heavily resists moving at all. Fluids, by definition, have no fixed shape and easily conform to their container. So why do some fluids fight back so aggressively when we try to move them? To find the answer, we have to stop looking at a volume of fluid as a single, solid chunk of matter. We have to look at its internal structure. This resistance is viscosity, the internal friction generated as infinitely thin layers of fluid slide past one another. This diagram shows a standard physics model isolating internal friction, a thin layer of liquid trapped between two flat glass plates. The bottom plate is locked firmly in place, while the top plate is pulled right at a constant velocity. In fluid dynamics, there is a rule called the no-slip condition. It dictates that any fluid particles physically touching a solid surface will stick to it completely. Because of this rule, the absolute bottom layer of our liquid, the molecules physically resting against the stationary lower plate, has a velocity of exactly 0. Conversely, the topmost layer of liquid is physically touching the moving upper plate. That means it perfectly matches the plate's forward velocity. Since the top and bottom boundaries move at vastly different speeds, the fluid trapped in between is forced to shear itself apart. What exactly is happening mechanically to the infinite horizontal layers of fluid caught between these two extremes? Imagine a thick book resting on a table. Lay your hand flat and push the top cover forward. The pages slide over each other, fanning out in a stepped diagonal slant. The fluid behaves exactly the same way. As the fastest top layer moves forward, it exerts friction to pull the liquid layer immediately beneath it along for the ride. But simultaneously, that second layer is being heavily dragged backward by the slower third layer beneath it. This diagram illustrates what physicists call a velocity gradient. The speed of the fluid drops uniformly, step by step, from the fast-moving top boundary down to the stationary bottom. If we apply this gradient to our initial experiment, the oil's internal layers slip past each other with ease. The honey's internal layers exert a massive frictional grip on one another. Viscosity is the physical cost and energy required to force these adjacent, microscopic sheets of fluid to slide past one another. If you apply shearing force to a solid object, it bends into a new permanent shape, but fluids continually deform as long as force is applied. Because the layers keep sliding, the physical stress depends entirely on the rate of strain. This layout shows the formula for the coefficient of viscosity, represented by the Greek letter eta. It calculates how much a fluid resists motion by finding the ratio between the shearing stress applied and the rate of the resulting shear strain. The takeaway is simple. The harder and faster you try to force those fluid layers to shear, the more aggressively the internal friction fights back. This coefficient gives scientists a universal number to predict exactly how much mechanical force is required to move any fluid in existence. This data table displays the viscosity coefficients for several common fluids, proving why completely frictionless fluid flow exists only in textbooks. Look closely at human blood. It has a significantly higher viscosity coefficient than water. That extra internal friction is why the human body requires a dense muscular heart to pump it through our veins. We can also see how heat manipulates this friction. As a car engine warms up from 16 to 38 degrees Celsius, the viscosity of its machine oil plummets, allowing the layers to slip faster and lubricate the moving metal parts. Compare those highly functional numbers to the extreme coefficient of honey, and the sluggish result of our initial gravity drop makes perfect mathematical sense. Every time a fluid flows, pours, or pumps, its internal layers are rubbing together.